If you want to know if an object is in one piece, your instinct is to look at its geometry. You look for the physical material binding it together, the distance between its molecules, the metric that keeps it intact. But topology discards distance and geometry entirely. Without a metric to measure the glue holding a shape together, topologists take an inverted approach. We don't look for what connects a space. We define a space as connected strictly by proving it is impossible to slice it apart. Looking at the formal definition here, a separation of a topological space X is a pair of two sets, U and V. The rules for these sets are absolute. They must be open. They must be disjoint, meaning they share exactly 0 points. Neither set can be empty. And finally, their union must perfectly reconstruct the entire original space, leaving nothing out. Because connectedness is defined by a negative, the lack of a separation, proving a space is connected requires a proof by contradiction. We must intentionally assume a valid separation exists, and then demonstrate that this assumption causes the mathematics to collapse in on itself. Topological connectedness is not a physical bond. It is a state of mathematical unity dictated entirely by the strict boundaries of open sets. To see how strict this definition is, we can test it against the rational numbers. The rationals are infinitely dense. Pick any two fractions, no matter how close, and you can average them to find another fraction perfectly nestled between them. Zoom in forever, and you will never find empty space. Visually, it looks like a continuous solid line, but we can break it. All we have to do is choose an irrational number, like the square root of 2, and use it as a scalpel to slice the space. Looking closely at example 4, we define two open sets. One captures all rational numbers from -infinity up to our irrational boundary a. The other captures all rationals from a to +infinity. Both sets are open. They are disjoint. And because the square root of 2 is irrational, it simply doesn't exist within the space of rational numbers. Our two sets capture every single rational number that exists, without ever overlapping or sharing a limit point. Despite being packed infinitely tight, the rational number line is full of microscopic gaps. Under the rules of topology, it has been cleanly separated. The rational numbers are completely shattered. If infinite density isn't enough to hold a space together, we have to look at the complete real number line. What specific structural property prevents the real numbers from fracturing the way the rationals did? The answer has nothing to do with addition, multiplication, or algebra. It depends entirely on how the elements are ordered. This definition block outlines the two rules required for a space to resist separation. Such a space is called a linear continuum. It must be dense, like the rationals, and it must possess the least upper bound property. The least upper bound property dictates that if you have any non-empty subset with a ceiling, an upper bound, there must be one specific point that acts as the absolute supremum, the tightest possible ceiling. This is exactly what the rationals lacked. If you look at all rational numbers below the square root of 2, you can always find a fraction slightly closer to the boundary. There is no single maximum rational number that caps the set. Any set that acts as a linear continuum is guaranteed to be connected. The rigorous part for us is proving exactly how that single least upper bound makes a topological separation mathematically impossible. We start by attempting the impossible. We assume a convex subspace of a linear continuum can be perfectly separated into two disjoint, non-empty open sets, which we will call A and B. We choose a point A inside set A and a point B inside set B. For this proof, we only need to look at the closed interval stretching from A to B. Following the rules of a linear continuum, we look at all the points belonging to set A within this interval. Because they are bounded by B, they must have a least upper bound. We define a new point, C, as that exact supremum. Because A and B separate the entire space, point C has to land in one of them. It cannot float in the void. We have to test both possible locations. Case 1. Looking at figure 24.1, we first assume point C falls into set B. Since B is an open set, it must contain an open interval around C. This means B extends slightly to the left, reaching some point D. But if D is in set B, it acts as an upper bound for set A, and D is strictly smaller than C. This destroys our premise. C was defined as the least upper bound. It cannot be in set B. Case 2. Shifting our focus to figure 24.2, we drop point C into set A instead. Because set A is open, it must also contain an interval extending to the right of C, reaching a point A. The density of the continuum guarantees another point, Z, exists perfectly between them. That places Z inside set A, but higher than C. If there is a point in A greater than C, then C isn't an upper bound at all. Placing the boundary point in either set triggers an immediate mathematical contradiction. The assumption that a separation exists is demonstrably false. A linear continuum cannot be cut. Driven by its supreme boundaries and endless density, the real number line is structurally unbreakable. When we prove a space is mathematically connected, human intuition immediately inserts a geometric bias. We assume that if a space is whole, you should be able to draw a continuous line from any point inside it to any other point. Looking at the definition provided here, topology formalizes this bias as path connectedness. A path is strictly defined as a continuous map from a closed interval in the real line into the topological space. The logic here flows cleanly in one direction. If you can bridge every pair of points with a continuous path, the space is definitively connected. But does the reverse hold true? Is it possible for a space to be completely unseparated, yet actively reject a continuous path between its own points? To answer that, topologists point to a famous anomaly, a mathematical structure designed to weaponize limits, breaking spatial traversal while maintaining absolute topological integrity. It is known as the topologist's sine curve. Looking at figure 24.5, the base of the shape is generated by graphing the equation y equals sine of 1 over x, for all x values strictly greater than 0. As x approaches the y-axis, the curve begins to oscillate faster and faster. The crucial step is completing the shape by taking its closure. We add all of the curve's limit points resting perfectly on the y-axis, a solid vertical line segment from -1 to 1. A foundational theorem states that the closure of a connected set is also connected. Because the original sine curve is unbroken, this new compound shape is verified to be topologically whole. Now we test the path. We attempt to draw a continuous route starting exactly at the origin, moving off the vertical segment and on to the oscillating curve. For a mathematical path to be continuous, the sequence of points it traces must eventually converge onto a single definable limit. But as our path attempts to leave the origin, it encounters the infinite oscillation of the sine curve. The y values violently alternate between 1 and -1. The sequence never settles. It never converges. The continuity of the path simply breaks. The topologist's sine curve stands as a single, unbroken entity, where physical travel across its own structure is mathematically impossible. It proves that in pure topology, connection isn't determined by the presence of a bridge. It is defined entirely by the absolute, rigorous absence of a border.